now going to take a look at some practice diploma questions for the thermochemistry unit. So let's take a look at question number 1. This says the balanced equation that represents the combustion of ethanol is blank and the sign of enthalpy change for the reaction is blank. Now there's a few things we need to keep in mind. That the combustion of ethanol, now the combustion of basically anything will give us an exothermic reaction. So exothermic reactions have a negative enthalpy. So the sign of the enthalpy change for this reaction is going to be negative. So I can definitely rule out B and D as options right off the get-go. Okay, then when it talks about my balanced equation that represents the combustion of ethanol, I'm going to be looking at my ethanol, okay, which is C2H5OH, and I'm going to be combusting it in oxygen, and I'm going to get carbon dioxide gas and water vapor as a product. So when I take a look at these two options that I have, either A or C, I just need to now find my balanced chemical equation. If we take a look at A, I see I have 2 carbons on my reactant side, 2 carbons on my product side. I see that I have 6 hydrogens on my reactant side, and I have 6 hydrogens on my product side. I have 7 oxygens on my reactant side, and I have 2 times 2, which is 4, and 7 oxygens on my product side. So I would say that A is my correct answer. Let's just double check that C is not correct. And when I take a look, I see that I have 4 carbons, 4 carbons. I have 12 hydrogens on this side, and I have 12 hydrogens on this side. And with my oxygens, I have 15, 16 oxygens, and on this side, I have 8 plus 6, which is 14. So we have not equal amount of oxygens. So C is also ruled out. Perfect. Let's move on. Question 2 says, which of the following diagrams represents the combustion of methanol in a closed system? Now again, because we're talking about combustion, we're talking about an exothermic reaction, which again will have a negative enthalpy change. So immediately when I see the values positive, it cannot be A, as well as positive, it cannot be D. Because it's exothermic, let's just see what we have to look at here. It says methanol is used as a fuel in racing cars. The energy content of methanol can be determined by calorimetry in a closed system. So again, we can rule out A and D, no problem. And let's just take a look between the answers B and C. So when we take a look, we see that both have the same reactants and products, but what we're looking at is these values of our enthalpy. So we need to actually do some sort of calculation in order to get our enthalpy change for the combustion of methanol. So when I go to solve this, I'm going to use my molar enthalpies of reaction formula, which states that my change in enthalpy is equal to the sum of my moles times my molar enthalpy of my products, okay, so my products minus the sum of my moles times my molar enthalpy of reaction of my reactants. Okay, so we're going to take a look at these. We're going to have to look at our data booklet, and we're going to need to get the molar enthalpy of methanol, carbon dioxide, and liquid water. Okay, so I know a few of these values off the top of my head, so we're going to start with those. So our products is going to equal 2 moles times our negative 393.5 kilojoules per mole. Okay, and this is for carbon dioxide. We're going to add our water vapor, or liquid water, pardon me, so we have 4 moles times our negative 285.5 kilojoules per mole. Now again, these values I just know off the top of my head. If you don't know them, they're in your data booklet, so no worries there. Okay, so there's our products minus our reactants. Now our reactants, we have 3 oxygens times 0. Okay, so that's just 0, plus our enthalpy of methanol, and I do not know methanol, so I'm going to need to jump over to my data booklet, oopsies, and get my enthalpy of methanol. So like I said, carbon dioxide was here at 393.5. My water was down here at 285.8 or 285.5 in what I put, and our methanol is negative 239.2, negative 239.2. Okay. So this is our 2, oops, changed my color there, 2 times our negative 239.2, I believe. Hopefully I didn't mess that number up. 239.2 kilojoules. Again, kilojoules per mole. So when I go to simplify this, I find that I have 2 times my negative 393.5 plus my 4 times my negative 285.5, or 2, actually it was 0.8. I should make that little correction here. This is a, oopsies, this is an 8. So when I do all of that calculation, I get that this equals negative 1930.2. And I'm going to subtract that from, oh boy, what's happening here? There we go. I'm going to subtract that from 2 times negative 239.2, which is equal to negative 478.4. And when I do that, I get negative 1,451, or, oh boy, this is, my pen is messing up here. There we go. Here, let's try that again. Negative 1,451.8 kilojoules of energy. So when we solve for that, we see that our correct answer is in fact going to be letter C. Okay, so again, we had to simplify and solve for this. Now, when I look at these values, it looks like this value is actually for 1 mole of methanol. So if you didn't multiply by your moles here, okay, so I'll circle them. If you didn't multiply by your moles, you wouldn't have got the correct answer. You would have got half of this answer. So be careful when you're doing that you solve using your moles times your molar enthalpy for this question. Okay, let's take a look at the next one. So this is numerical response number 1. It says, use the following information to answer the next question. It says the enthalpy diagram above can be used to represent the reactions numbered blank. So let's take a look. What I see with this reaction, I notice that my reactants are down here, my products up here, and I have my potential energy diagram. What I notice is that this is then going to be listed as an endothermic reaction, okay, which means that my change in enthalpy is going to equal a positive value. Okay, so when I go to look at what answers could be possible, I know that I'm going to have an endothermic, it's going to be a positive, and we're going to see what ones it could potentially refer to. So formation of carbon monoxide, it has a negative enthalpy, no can do. Okay, and also this, sorry, before we get going too far, also energy would be listed as a reactant in an equation. Okay, so then we look at formation of nitrogen monoxide. I see that as a positive value. That is a good sign. Okay, we have a negative value again, a positive value. So far we have numbers 2 and 4. We see that number 5 has the energy listed as a product. Therefore 5 is cancelled out, crossed it out. 6, we see that it is listed as a reactant. We see energy as a reactant, therefore it is an endothermic reaction. Okay, and what we see here is that our 7 has a positive value, again, meaning it's an endothermic, and 8 is a no-go. Therefore, we have 2, 4, 6, and 7 as our correct answers here. So when I go to write them in, it says in any order, so 2, 4, 6, and 7, and when I record them in my answer sheet, it shouldn't matter the order that I put those in as. Let's continue on. So, multiple choice number 3 says, the molar enthalpy of reaction for nickel oxide in the reaction represented above is blank. So, when we take a look at this question, we can go and look at the total enthalpy produced in this equation. Now, when we're looking at the molar enthalpy of reaction, which means that it is specific to this reaction, okay, we can look at how many moles of nickel oxide we have, and the total energy that we have. So we can look at this equation. We can look at our enthalpy of reaction is equal to our moles times by our molar enthalpy. And since we know that our enthalpy of reaction, I will just actually do this. We know that we have positive, it's a product, so we have negative kilojoules equals how many moles of nickel oxide we have times x. So when I simplify for x, I go x equals 3 divided by negative 954. And when I solve for that, I get that this equals negative 318 kilojoules. Okay, again, because this is the, on the product side of things, it's a negative 954 kilojoules for this reaction, meaning that it's kilojoules per mole here. So our correct answer for 3 should be C. Simple enthalpy calculation for that one, so don't get too tied up in that question. Okay, this question says the mass of methanol, that burns to produce an enthalpy change of 9 times 10 to the 4 kilojoules of energy is blank kilojoules. Okay, so let's take a look at this equation and see if we can go about figuring this out. So what we see here is this is our overall reaction, and essentially we're going to solve to find moles of enthalpy. So what we want to do is we want to look at our reaction like this. Again, if our enthalpy of reaction is equal to our moles times by our molar enthalpy, okay, we can solve for however many moles that we have. Now, our first goal is to get how much our enthalpy of reaction for this reaction is for 1 mole of methanol. So our molar enthalpy of reaction, for methanol is going to equal negative 1,275.8 kilojoules divided by 2 moles. Okay, that is going to equal negative 637.5 kilojoules per mole. Now that is my molar enthalpy of methanol, or the combustion of methanol. And I guess I can change all of these little letters to a C. Okay, so now that I have my molar enthalpy of combustion for this reaction, I can work backwards to solve for my enthalpy of reaction using this much energy. So in this case, I'm going to go back to using this formula here, and I'm going to say that negative 9.0 times 10 to the 4, kilojoules is equal to moles, whatever our value for moles is, times by my molar enthalpy being negative 637.5 kilojoules per mole. So when I go to solve for this, I need to divide my negative, here I'll do this like this, and need to divide by my negative molar enthalpy, and which means I'm going to divide by the same value on this side. Those cancel out, giving me moles. So when I do that, I get I get a value, a molar value, moles is equal to 141.18 moles. Now, since I'm looking for my mass, okay, I need to look for my mass. Now, you have to remember that mass is equal to moles times by my molar mass. So I have my moles here, and my molar mass of methanol is equal to carbon is 1 times 12.01. Hydrogen is, I have 4 hydrogens, so I have 4 times 1.01. And I have oxygen. I have 1 oxygen, which is 16. Now, all these values, again, are off your data booklet, so you should be able to figure that out. So I get 18... let's do this here this way. 12.01, 4.04, and 16.00, 501, so 32.05 grams per mole. There we go. So when I do this calculation, I have my 141.18 moles times by my molar mass of being 32.05. Okay, I get a value of 4,524 grams. Okay, actually it's 24.7, but that's okay. Now I get grams. Now because this is asking for my units in kilograms, okay, that's very important to make sure you're doing this. It says record your 3-digit answer. So 3 digits also means we have to have 3 digits plus a decimal in there because you have 4 places to respond in your answer sheet. This means that I have to move my decimal 1, 2, 3 places over to the left, meaning my answer is 4.52 kilograms. Okay, as you can see, this is a multi-step, this is a 4. This is a multi-step question. We needed to start by solving for my molar enthalpy. Once I found my molar enthalpy, I could find my number of moles. Once I solved for my number of moles, I had to find my molar mass and calculate my mass from that molar mass calculation. Okay, so this is how you would go about solving this question. Okay, let's go to the next few here. So this says, in an experiment, technicians compared the use of methane and propane as fuels. They burned samples of the 2 fuels and used a calorimeter to determine the energy transferred. The combustion reactions are represented by the equations below. Then it says, which of the following statements correctly classifies the 2 variables in the technician's experiment? So, the manipulated variable is the type of fuel, and the controlled variable is the type of calorimeter. Well, that sounds pretty good. I'm going to put a check mark beside those. That sounds correct. Okay, the responding variable is the final temperature of the water, and the controlled variable is the type of fuel. Now, the controlled variable isn't the fuel. The controlled variable is the thing that remains consistent across all of the tests. So the type of fuel should be the manipulated variable. So I'm going to put an X through B. Okay, the manipulated variable is the type of fuel, which is correct. And the responding variable is the temperature change of the fuel. Now, this isn't quite accurate either because the temperature change isn't calculated of the fuel. The temperature calculated is of the water, so of the calorimeter, okay, or whatever entity is being absorbed by the calorimeter. So C doesn't quite make sense either. Okay, so we see the responding variable is the final temperature of the water, which should be correct, and the controlled variable is the temperature change of the fuel. Again, we cannot change or adjust the temperature change of the fuel. However, we can give the fuels a certain activation energy, but the temperature change is not going to be something that we can control. So the correct answer here is A. Okay, our 2 favorite endo and exothermic reactions are photosynthesis and cellular respiration. So it says, which of the following statements accurately describes photosynthesis and cellular respiration? Okay, a few things to notice when you go through these equations, okay, is that we have a reverse reaction. Here we have energy input, meaning that this is an endothermic. Here we have energy output, which means that this is an exothermic. Okay. When we take a look at this, generally, if we see this style of question, especially referring to photosynthesis and cellular respiration, the thing that we need to keep note of is the form of water. Okay, so in both of these equations, we're saying that we have liquid water produced. Therefore, if we were to use our molar enthalpies of formation, we would get the exact same molar enthalpies of formation, except this would be a positive value. This would be a positive value. And this would be a negative value. Okay, but the values would be equal. Just different signs on them. Okay, so because we have liquid and liquid, that is the biggest thing that we need to pay attention to. If they give you an example where in photosynthesis we're dealing with liquid water and in cellular respiration we're dealing with water vapor, we need to be careful as to comparing these values because they will not be equal. They will still be negative and positive, but they will be slightly different because the molar enthalpy of formation of water vapor, if we use it in cellular respiration, is negative 241.8, where liquid water is negative 285.8. So the values are slightly different. In this case, though, we don't have to worry about that, and we can take a look at which of these answers makes the most sense. In this question, I would say that when it says the products of photosynthesis have less potential energy than the reactants, whereas in cellular respiration, the reactants have less potential energy than the products. Okay, so in cellular respiration, we actually expect the reactants have more potential energy than the products because we have an exothermic reaction. So A doesn't quite make sense. Okay, photosynthesis traps the energy in the form of glucose, and cellular respiration absorbs the energy required by all organisms. This one also doesn't make sense. That's not really accurate at all. Okay, photosynthesis is an exothermic reaction. Well, we just said up above that it was endothermic, and cellular respiration is endothermic. Where photosynthesis requires energy and cellular respiration produces energy, that sounds pretty good as an answer to me. And especially it is what we see in this equation. So 5D is the correct answer here.